The system, the University of British Columbia Unmanned Aircraft Systems design team from Vancouver, Canada, will be bringing to the AUVSI 2022 competition consists of a heavy lift quadcopter named a Taxac with an MTOW of 14 kilograms, a winch-lowered autonomous rover named Wally weighing under 2 kilograms, a high-quality live image capture system that streams video over cellular networks for manual ODCL, custom onboard software running on an ODroid for active aircraft avoidance and obstacle detection, the open-source ArduPilot firmware for autonomous waypoint navigation and control, and a custom ground station for waypoint routing and monitoring aircraft. With this system, we will be attempting autonomous flight and waypoint navigation with a confidence of 99%, obstacle avoidance for both stationary and moving obstacles with a 70% confidence, manual object detection, classification, and localization with a 75% confidence, and airdrop with an 85% confidence. We will not be attempting the mapping task due to time constraints in the chosen mission strategy. The main testing methods employed differed by the systems: mechanical, electrical, software, and mission tests. The mechanical systems were tested first using simulations, such as finite element analysis, and then validated with physical stress testing in system tests. The electrical systems were bench tested and endurance tested in mission tests with the applicable loads to validate their performance and reliability. Software was first tested using software-in-the-loop systems that reflect our system software, and unit tests to validate functionality before being tested for integration and real-life flight applicability in full system tests, once the mechanical and electrical systems were ready. These methods of testing allowed us to design a system that would meet the requirements with some safety margin and validate the designs through physical, vehicle, and system tests. They also allowed the concurrent development and testing of the aircraft and payload systems with the software and communication systems integrated at later stages. The team conducted 2 fully autonomous flights this past year to verify that the system still performed as it did in previous years with the same airframe and setup. The first of these flights was a 20-second autonomous takeoff to a predetermined altitude, followed by a 25-second manual landing. The second flight was a fully autonomous waypoint mission. The UAV took off autonomously and followed waypoints for 7 minutes before landing manually in approximately 25 seconds. From these flights, the average time spent in manual mode per flight is expected to be approximately 50 seconds. The aircraft's PID values were tuned initially by flying it manually and looking at graphs, followed by using an auto-tune block for finer tuning. The aircraft was also tested for different cruise speeds to determine the waypoint travel speed. Given the default landing speed parameters, the team set up an impact stress simulation with the UAV's landing gear CAD and found that it would adequately dissipate the impact. Waypoint performance was gauged by reviewing log files from the aircraft after the second autonomous flight. The aircraft attempted a 10-point mission and successfully visited 10 out of 10 mission waypoints. The average waypoint miss error in feet was calculated to be approximately 6 feet. 9 simulated missions were prepared in order to test all possible cases for obstacle avoidance. The avoidance algorithm was developed with this testing suite of 9 missions in mind at all times. In addition to static obstacles, the team also developed software for simulating active aircraft as dynamic obstacles. The avoidance algorithm has passed 9 out of 9 of our simulated mission tests and has repeatedly shown to be capable of rerouting the aircraft in under 5 seconds. A variety of camera configurations were experimentally tested in order to ensure that our UAV used the highest possible image resolution. We started with 3 GoPro cameras to compare, one Hero 5 Black, as well as a backbone-modified Hero 3 Plus and Hero 6 Black. The lowest resolution Hero 3 Plus was ruled out. We found that the stock lens on the Hero 5 was too wide to make out details at distances greater than 13 feet, but we continued using it in testing as a baseline. Some lenses for the Hero 6 were quickly ruled out. Our fisheye lens faced the same issues as the Hero 5, and our telephoto lenses didn't allow us to see enough of the area below. This left us with 2 main lens options, one with a focal length of 4.5mm and another with one of 5.4mm. We performed an image resolution test at about 80 feet between the 2 lenses as well as the Hero 5. The test was conducted using scaled-down versions of the letters that will be found at the competition. It was found that the Hero 5 averaged an object resolution of 60 by 60 pixels. The 4.5mm lens was around 80 by 80 pixels, and the 5.4mm lens was about 105 by 105 pixels. This test led us to pick the 5.4mm lens, as it has twice the resolution of the 4.5mm and 4 times the resolution of the Hero 5. In order to run accurate tests, sample scaled-down ODCL objects were created by the team. Next, 4 sets of 6 images were collected in order to test the image detection and classification software at different altitudes and exposure levels. Although the team will be relying on manual classification at the competition this year, the detection solution is autonomous. The detection solution will generate isolation masks to separate ODCL objects from grass at altitudes of up to 165 feet. When the original 4K images are correctly exposed, the algorithm achieves an accuracy of nearly 70%. Every image taken by the UAV is immediately geotagged. The geotagged location has an accuracy of 8 feet. For simplicity, the object is assumed to have the same position as the UAV. The team ran one full airdrop test from the aircraft hovering at the planned mission altitude. The payload was able to survive this drop and landed 4 feet away from the target. Other unit tests were performed on the system, including non-flight drop tests to ensure winch and rover security, winch flight tests with a simulated load to test reliable winch operation and ensure that the rover will be safe, and several autonomous rover GPS waypoint navigation tests during the development of the rover navigation system, which ensure the rover's accurate positioning. During GPS waypoint navigation testing, the rover was able to come to a complete stop consistently within 1 meter of the target location. The team has performed several flight tests in order to test completion of the different tasks that we will be attempting during the competition flight window. A total of 21 flights were performed this year, which complements the testing that was performed in previous years on the same aircraft system. Of these flights, 6 of the flights were mission simulations of the tasks. 1 flight was dedicated to ODCL tasks, 2 flights were dedicated to autonomous flight, 1 flight for airdrop, 1 for waypoint navigation, and finally a flight where all of the intended mission tasks were flown as in the competition window. Each of these flights were timed and flown accordingly to the estimated mission timeline. A flaw in the live image transmission was identified during an ODCL task flight, as the Bullet 2.4 GHz connection between the ground station and aircraft had insufficient bandwidth for the image size. This prompted a switch to using cellular data, which was flight tested several times with proven image results before being flown in the full mission successfully. In previous years, the waypoint navigation, airdrop, and imaging have been tested. This development year, there was an emphasis on also completing the ODCL task and improving the airdrop system for greater accuracy. Based on the calculated score from the mission test and average results from several individual task tests, we took the average of the scores and multiplied them by our % confidence in each task completion. We believe we can achieve a total of 62.5 points out of 100 for the mission demonstration based on the testing we have performed.